In this video, we're going to learn how type 1 factoring can be seen also as special cases. Look at part 1. Let's go ahead, do what we learned yesterday and factor it. So we're looking for numbers that multiply to 25 that add up to my middle value b, which is 10. Those numbers are 5 and 5. So my factors are x plus 5 times x plus 5. The reason why it's special is because these are the same. We could rewrite this as x plus 5 squared. We call this a perfect square trinomial because the binomial factors are exactly the same. Now, as a quick review, remember, back in the day, some of you thought that x plus 5 squared was x squared plus 25. You would think that you would just distribute. You can't because there's a plus sign. Now it's going to make sense to you even more because x plus 5 squared is x plus 5 times x plus 5. So when you distribute and you FOIL, you could see that you should always have that middle term. So again, as a review, remember when you have x plus 5 squared, it does not equal x squared plus 25. There is a middle term. Now, we're going to factor. When we factor, we're going to make sure we focus on looking for a GCF. A lot of the times when we factor, we just go ahead, we do a T-chart, and we figure it out. That is a problem because the first thing we did in this unit is finding greatest common factors. You always want to pull out the greatest common factor before you even consider a T-chart. So let's look at number 1. You first look for a GCF. So first, always a GCF. In number 1, there is none. So then we could go ahead. We see A is 1. We're finding numbers that multiply to 16 that add up to 8. That is 4 and 4. So hopefully you're like, oh, it's a special case. The reason why they call it a special case because there's a special name for this. This is a perfect square trinomial. You may write it separate or you may write it together. They're the same to me, guys, so I'm okay with it. I believe your answer key will have you write it as x plus 4 squared. Number 2, no greatest common factor. We're looking for things that multiply to 100 that adds up to negative 20. Those numbers are negative 10 and negative 10. You could see that again, it's a perfect square trinomial, and you could write it, if you would like, as an x minus 10 squared. Look at the C values. What do you notice about the C values? The C values are perfect squares by themselves. Now, it doesn't guarantee that you're going to have a perfect square trinomial, but when you see a perfect square as a C value, look at it. And then usually a rule of thumb is if you take the square root of it and double it, it should be the middle term. Now you got to watch your signs, but think about 100. If I took the square root of 100, I get 10. And if I double it, I get 20. Notice that's my middle term. If I take the square root of 16, that's 4. If I double it, I get 8. Now this is just a quick way of seeing it. You do not have to do it this way. You could just continue with the T-chart and not worry about the short way of doing a perfect square trinomial. But I want you to see this. These are pretty special, and that's why they're called special cases. Let's move on to number 3. Number 3, first of all, it's not even a quadratic. It's a linear term with 2 terms, so it's a linear binomial here. And the only thing we could do is pull out a GCF. Both of these numbers, 4 and 6, have a 2 in common. Now, if I pull that out, there's no way of factoring this anymore because I don't have an x squared or a quadratic. So it's just a GCF problem. Let's look at number 4. All of these values could be divisible by 2. If I pull out a 2, I get x squared minus 10x plus 24. And just to think about what I talked about previously, this 24 is not a perfect square, so I shouldn't have a perfect square trinomial. However, if I look what's left over, it looks like I might be able to factor this, and I'm going to go ahead and make a T-chart. What are numbers that could possibly multiply to 24 and adds up to 10? Now, if it works, it's great. If not, then that would be my answer, just taking out the GCF. But we could factor this. a -6 and a -4 will make this true. Don't lose the GCF. It's still a part of the factoring. Write your factors. Remember, your factors, when multiplied together, should be the original problem, which is the product. If you drop that 2, you're not going to get that 2x squared. So the GCF stays, and then you factor the trinomial. Let's look at number 5. Number 5, it has a GCF of a 3. We pull out a 3. We have x squared minus x minus 1. Now, this could be a perfect square trinomial because 1 is a perfect square. But let's see. Is there anything that multiplies to -1 that adds to my middle term -1? Well, the only things that multiply to -1 is -1 times +1. And when I add those, that makes 0. So that means this is prime. However, the problem is not prime. The problem had a GCF, so that is going to be my factored form. Just the GCF, and then my trinomial stays. Would I like for you to pause the video, try 6, 7, and 8, and then we'll check your solutions. Okay, for number 6, you start with the GCF. If you look at it, after you pull out the 2, you could see that 9 is a perfect square. So it could possibly be that the binomial factors are the same. I checked it with the T-chart. I noticed it was a perfect square trinomial. Remember, you could leave it expanded or you could put it together. Number 7, I again pull out a GCF. The greatest common factor was 3. And then notice that -24 was not a perfect square. However, it was still factorable. Multiplies the -24 that adds up to 2 are +6 and -4. Remember, do not lose that GCF. And number 8, pull out your greatest common factor 4. Look at your C value. Notice it's a perfect square. The factors might be the same. Tried the T-chart. They were. So it was a perfect square trinomial. And again, you could leave it separated, or if you choose to do so, put it together. Now, we have one more special case that we're going to talk about. Let's look at part 2 and again do the T-chart. Now, the thing about the T-chart is it should multiply to A to C and add up to B. I don't have a B value, so if you think about it, it's a 0. So I'm going to write it out. I'm finding numbers that multiply to -49 that adds up to 0. Those numbers would be -7 times +7, -7 plus 7. That would add up to 0. So I get x minus 7, x plus 7. Now, these are not perfect because they're different. When they're different, that is called a difference of 2 squares. It is because the middle terms cancel, which is why b is 0. And when we do it, the 2 terms that we get are going to be subtracted, and both can be written as a square of something. If you look at factoring the difference of 2 squares, it's really easy to do. You got to make sure they're both perfect. So the example we have up front is part 2. We have x squared minus 49. You would say, okay, what is the square root of x squared? What is the square root of 49? You take those that you found and you always add them and you subtract them. The sign should always be different. The reason is because the middle term should be 0. So when you do the difference of 2 squares, if I have a squared minus b squared, it always has to be a minus. You take the square root of them and you will get a plus b, a minus b every single time. Now, if there's a 4, like if it's a to the 4th or b to the 4th, you would again take the square root, but then you might have to take the square root again. They could even get bigger. But don't forget, different signs, ladies and gentlemen. And you take the square root of each term to figure out your a and your b. Let's look at number 1. Always GCF 2. Don't forget, I'm going to always write first GCF, and then we could talk about those special cases. And number 1, we don't have a b value. That is how we know it could be a difference of 2 squares. And then we check. We can see the sign is negative, which we need. and then we take the square root of each. The square root of x squared is x, the square root of 16 is 4. We write them, and then we add and subtract them. And number 2, we can clearly see there's a b value. That means it is not going to be a difference of 2 squares here. We're going to go ahead and do the t-chart. However, look at 16 is a perfect square. So that perfect square could mean my binomial factors might be the same. What multiplies this 16 that adds up to -8? Those numbers are -4 times -4. It works for both. So it is a perfect square trinomial. So as our key words, this is called a perfect square. And this is called a difference of 2 squares. They sound a lot alike, but the way to remember it, perfect squares means they become perfect. They're squared. And a difference means, well, different means different sign. So the vocabulary really helps for you to remember it. Let's look at number 3. Again, GCF first. So we're going to pull out a 2. I'm left with x squared minus 1. Now, don't think difference of squares first. You always pull out the GCF. Now I'm going to focus on possibility of being a difference of 2 squares because my b here is 0. So can I take the square root of these? Are they both perfects? They are. So the 2 stays. The square root of x squared is x. The square root of 1 is 1. And then I add them and I subtract them. All right, number 4. GCF first. I could see I could pull out a 3 and also an x. If I pull that out, I would need 2 x's to make a 3x cubed and a -9 to get that -27x. Again, b is 0, and if you think about it, these are both perfect, so it's going to be a difference of 2 squares. They need to be perfect, otherwise we can't take the square root. So what is the square root of x squared? X. What is the square root of 9? 3. Now, if you can't take the square root, ladies and gentlemen, that means that would be my answer. It would be factored. But because I could take the square root of these, we continue because we know it's a difference of 2 squares. Okay, so just because b is 0 does not mean it's going to be a difference of 2 squares. Don't forget that. Let's go ahead and look at number 5. First thing is GCF. Pull out the 5. I have x squared plus 10x plus 5. Now, what's left over here is a trinomial. This is not perfect, so we're going to check the t-chart. Is there anything that multiplies to 5 that adds up to 10? 5 times 1, 5 plus 1. That doesn't work. So this is only a GCF problem, okay? Number 6. I have b is 0, and if you look at these are perfect. So we're going to take the square root. The square root of x squared is x. The square root of 25 is 5, and the square root of y squared is y. So in my head, I'm taking the square root of these. It's a difference of 2 squares because these are both perfect, and b is 0. Then we take those 2 values, and we add them, and we subtract them. Number 7 is pretty special because we have x to the 4th. Again, b is 0, and both of these are perfect squares. So I'm going to take the square root of both of these. Now, the square root of x to the 4th is x squared, and the square root of 81 is 9. Now, I'm going to add them, and I'm going to subtract them. Think about what you just did. You made another perfect square. X squared plus 9 is not a perfect because there's a plus sign. But a minus is a difference of 2 squares. There should always be a minus in the middle. So I keep the x squared plus 9 because it's still a factor. But I could break x squared plus 9 as x plus 3, x minus 3. The reason, the square root of x squared is x, the square root of 9 is 3, and then we add them and we subtract them. Notice when you have a exponent that is bigger than 2 but still a perfect, all that means is you're going to get more factors. Last but not least on this page is number 8. I could see there's a GCF of a 3x, not a squared though because x is the highest. And if I pull out a 3x, I would need x squared to get that back and a plus 2. Now, if you look at this, b is 0, but this is not a perfect square, and there is an addition sign. That means it cannot be a difference of two squares, and that means this is just a GCF type of problem. All right, what I'd like for you to do is pause the video, and you have a closure. You're going to try these problems yourself, and then when you're ready, you could check your answers with mine. Please go ahead. Okay, number 1 is x minus 5 and x plus 2. Number 2 is x minus 8 and x minus 12. Number 3 is x plus 7 and x minus 5. And 4 is 7 plus x and 7 minus x. Now, I wrote a little note here. It matters that the 7 comes before the x's. The reason is the signs. This 49 is positive, so the 7 has to come first. The negative x squared has to be negative, so that has to be after. Now, I know I didn't really discuss this in other videos, but if you haven't realized this, and if some of you write it this way, these factors, and for instance, in number 3, it doesn't matter which one you write. These are the same. Because at the end of the day, if I go ahead and I distribute all of these and FOIL them out, we're going to get the same results. So please know that if you have numbers 1 or 2 and you wrote the x plus 2 first and the x minus 5 second, it's fine. These could be switched. What can't be switched is the signs. Okay, but in 4, it matters that the 7 comes first and the x comes last because the x squared is seen last. And you cannot put that first. In number 5 and 6, I went ahead in 5 and I factored each of them to figure it out. So you get A, D, and E. Notice B was prime. Remember, it's not a difference of two squares because we have a plus sign in the middle. It's got to be a minus. And then number 6, you take out a GCF and factor, and your answers are A and E. Okay, this ends the video for today.